Biphenyl. Biphenyl is a molecule made of these pieces, 12 carbon atoms and 10 hydrogen atoms, put together like this. A more streamlined way of depicting the molecule is with a skeletal structure. In a skeletal structure, the carbon atoms are replaced by kinks in lines, and the hydrogen atoms on them are implied. Biphenyl in nature occurs as an ingredient in natural gas and petroleum. Natural gas and petroleum are basically the crushed up guts of ancient microbes and plants and animals in prehistoric ecosystems. They're buried by sand over time, and so they get stuck deep in the belly of the earth. Some of them, though, find their way through the cracks in the rock of the crust of the earth and spill out onto the surface of the earth. Sometimes this occurs as the lightest of the hydrocarbons that made up the ancient plant and microbe guts, and those are gases. That's what natural gas is. There are a bunch of places on Earth where natural gas will just seep out of the ground. You'll have a vent of natural gas. Natural gas is flammable, and so you can light these vents of gas on fire, and they just burn continuously. And some of these have burned for decades. They're called eternal flames, and they occur in many places across the world. This one, for example, is in New York. And those gases that are burning there, one of the things that's in them is biphenyl. Biphenyl is also in petroleum, and this petroleum also can weave its way through the cracks in rocks in certain parts of the crust and start seeping out of the rocks at the surface of the earth. And so this black band here is petroleum that's seeping out of the rock. And here again you can see it spilling over the rocks. And in some places it can even collect, and it can get these collections of petroleum, really tar and oil. These collections can build up even into large lakes. This is not a man-made structure. This is a natural lake of petroleum and tar in Trinidad. So biphenyl is found in these petroleum and tar and natural gas sources and can be separated from them. Humans use derivatives of biphenyl for a bunch of different things. One is as an emulsifier. Oil and water don't mix. So if you pour oil into water, they'll separate into two layers. But there are some molecules you can add to these oil-water mixtures that allow them to mix. Those are called emulsifiers, and biphenyl can be used to make emulsifiers. Biphenyl can also be used to make molecules that whiten clothes. You might have some old clothes that used to be white and now they're turning a little yellowish. And what they can add to detergents are derivatives of this biphenyl compound. They absorb ultraviolet light, use some of the energy to wiggle around, and then emit a blue light. And you can see that happening here. This is the blue light being emitted by these biphenyl derivatives. And those will get stuck in your clothes, and by emitting blue light, it will sort of cancel out the yellowish colors, and the effect will be that it will look like it whitened your clothes. So clothes whiteners can be made from biphenyl derivatives. Biphenyl derivatives can also be used to kill fungi and molds, and that's especially important for crop production. So certain biphenyl derivatives have been used to protect crops, as can be seen in these crop fields in Kansas. Finally, there are some biphenyl derivatives, so not biphenyl itself, but some derivatives, the things you make from biphenyl, that can be used to then make plastics. When you think about the safety of a molecule, as with biphenyl here, a nice visual way to summarize the considerations, the things you want to think about, are these fire diamonds or safety squares. The blue square on the left represents the hazards a molecule presents to your health. It's on a scale from 0 to 4, where 0 represents no health hazard, and 4 represents a quick death on exposure. Biphenyl is a 1 on that scale. If it can cause eye irritation, so when you work with it, you want to make sure you wear goggles. It can cause skin irritation, so when you work with it, you want to make sure you wear gloves and a lab coat. And it can cause respiratory tract irritation, so you want to make sure you work with it underneath a fume hood. A sort of specific measurement that helps to communicate a molecule's toxicity is something called the LD50. In any population, some people are more frail and other people are more robust. And so the same dose of a molecule won't kill everybody. Instead, pharmacists and toxicologists use a measurement called the LD50, which measures how much would kill about half of everybody in a population. So this stands for the lethal dose for 50% of the population. This is how much, if you gave this dose to everybody, half of everybody would die. This is usually measured in rats, and so when biphenyl was administered to rats, it was found that 2,140 milligrams per kilogram of body weight would kill half of a rat population, and that's used as an estimate for humans. The red diamond at the top represents a molecule's flammability. It's also on a scale from 0 to 4. In this case, 0 means a molecule will not burn under any circumstances, and a 4 means the molecule is a flammable gas at room temperature. Biphenyl on this scale is a 1. There are two numbers that help to more specifically communicate what that means. One is called the flash point. This is how hot a molecule would have to be for a spark to be able to light it on fire. So the flash point for biphenyl is 113 degrees Celsius or 235.4 degrees Fahrenheit. If biphenyl is colder than this temperature, a spark can fall on it and it will not burst into flames. But if biphenyl is above this temperature, if a spark falls on it, it will burst into flames. That's the flash point. Another important number that communicates the flammability of a molecule to you is the autoignition temperature. This is how hot you'd have to get the molecule for it to spontaneously turn into flames. You don't need a spark, you don't need a lighter. If you get biphenyl this hot, it will burst into flames. And so that's 540 degrees Celsius or 1004 degrees Fahrenheit. This might seem like a really hot temperature, but a hot plate or a stovetop can easily get that hot. The yellow diamond on the right represents a molecule's instability or reactivity. It's also on a scale from 0 to 4. In this case, 0 means the molecule will not explode under any circumstances, and 4 means the molecule will explode at room temperature, if disturbed. Biphenyl is a 0 on that scale, so you can shake it up, move it around, it will not explode. Because the white diamond at the bottom is empty, it means there are no special considerations you have to take into account when you're working with biphenyl, except for the health, flammability, and instability considerations. Let's try to visualize biphenyl. As we saw, the skeletal structure, the streamlined way of depicting biphenyl looks like this. The kinks in those lines are representing carbon atoms that have hydrogens on them, but this is a two-dimensional representation of a three-dimensional molecule. Notice that each of the carbons in each of these rings is trigonal planar. It's triangular and flat. Also, depicted in this diagram are colors representing the charges on a molecule. Colored images of a molecule that represent where there are charges on the molecule are called electrostatic potential maps. Where electrons are accumulating, as in what look like double bonds here, they bring their charge with them, and you would expect to have a slight negative charge there. That's being represented by the red color. Where on the ends, where you don't have those double bonds, you get ever so slightly a lack of electrons, and that's represented by this blue color, representing the positive charge where electrons are missing. The green color in between is representing where the molecule is neutral. The significance of charge is it tells you where a molecule is sticky. Opposite charges attract. These bonds are not still. They're living, breathing, dynamic, twisting, turning, vibrating things. To help you visualize what biphenyl looks like as it moves in the world, as a real molecule, here's a simulation showing it vibrating, twisting, and turning. The simulation is playing at around 1 vibration per second, so you can visually track how it's moving. But at room temperature, those bonds would be vibrating and twisting and turning around 10 trillion times per second. Let's speed up this molecule just 20 times. Now let's speed it up 400 times. At room temperature, biphenyl would be moving more than 25 billion times faster than that last simulation. Each molecule, as you move from the microscopic world to the macroscopic, acts like a sort of pixel. And when you zoom out far enough, the point where we start to exist, we who are galactically large, once you get large enough on our size of the world, the biphenyl molecules start to merge together like pixels on a screen, and you end up getting a white solid, a white crystalline solid like you can see here. That's what biphenyl looks like at room temperature on the macroscopic scale. Those white crystals are huge populations of biphenyl molecules. Each crystal contains quintillions of biphenyl molecules. And when biphenyl accumulates like that into huge populations, those populations take on their own personalities. The personalities of populations of a molecule are called the physical properties of the molecule. You can look up the physical properties of biphenyl in reliable handbooks like the CRC handbook on the left or the Merck index on the right. One physical property that's important is the phase of a molecule. Is it a solid, a liquid, or a gas? At sea level, that will depend on the temperature. Below 156.6 degrees Fahrenheit, biphenyl will be a solid. Notice that includes room temperature. Between 156.6 and 491 degrees Fahrenheit, biphenyl will be a liquid. Notice you could reach those types of temperatures in an oven. Above 491 degrees Fahrenheit, biphenyl will turn into a gas. As a scientist, you don't just want to think in degrees Fahrenheit, you also want to think in degrees Celsius, this metric unit for temperature. So to restate that again, biphenyl will be a solid below 69.2 degrees Celsius, which includes room temperature. It will be a liquid between 69.2 and 255 degrees Celsius, and it will be a gas above 255 degrees Celsius. Compare this with water. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. You can use these freezing points and boiling points to separate molecules if they're in a mixture. For example, if biphenyl were in a mixture, you could cool that mixture down until biphenyl froze, and then you could strain the biphenyl out of that mixture. When you separate things based on their freezing points, on freezing, that's called crystallization. On the other hand, if you had biphenyl in a mixture, you could heat the mixture up so that biphenyl evaporated, and the other molecules didn't. You can then collect that vapor and have it drip into another container. When you separate things based on their boiling points, that's called distillation. A second physical property that's important is a molecule's solubility. It's significant because it creates structure within fluids. Let's think about the solubility of biphenyl in water at room temperature. Solubility, or whether molecules mix, really has to do with how charges are spread out over the molecules. Water has charges on every single atom in the molecule. Biphenyl has only light and partial charges. No atom in biphenyl is especially electronegative, so you're not getting these deep red, large partial charges like you do in water, or these deep blue, large partial positive charges. So the water molecules will tend to be much more attracted to each other, their big charges on each other, than to these partial, slight, small charges on biphenyl. They'll be attracted ever so slightly, but not very much. And specifically, 0.00445 grams of biphenyl, it's a very small amount, will dissolve in 1 liter of water. A final physical property you want to consider is density. Density is important because it creates structure based on sinking and floating. Cooler air, more dense air sinks, hot air, less dense air rises, and that creates winds. More dense rock sinks, less dense rock floats, and that helps to create the tectonic movements of the plates on the surface of the Earth. So density helps to organize things based on sinking and floating. The density of biphenyl is 1.04 grams per milliliter. Compare that with the density of water, which has a density of 1 gram per milliliter. Because the density of biphenyl is bigger, it would sink when you put it into water. Hopefully this video has given you a better understanding of the molecule biphenyl.